Hi, I'm Eric Woldridge, and today's presentation is a comparison of additive manufacturing and subtractive manufacturing with the use of finite element analysis to verify material efficiency through design. And kind of what we're going for with this project, as you see on the screen, are comparing a design solution that was designed with subtractive manufacturing in mind and comparing it with a similar design solution with additive manufacturing in mind. And we'll be using finite element analysis to make the comparison of where are we saving material, what design performance could be improved, those sorts of things. So the overall goal with this project is to really just evaluate how additive manufacturing can improve productivity through the purpose of material efficiency, and how we're going to use finite element analysis to actually sort of justify some of the results, or look at some of the results in comparison of the two. All right, so let's get started. First off, in terms of additive manufacturing, if you're not familiar with the process, it's often referred to commonly as 3D printing. And the material processes themselves, the process is different, although the material itself is very similar. For example, plastics are the same plastics we use in plastic injection molding in many cases. Metals that we can use with subtractive manufacturing are the same metals that we can use with additive manufacturing. So the materials themselves are the same, however, how we get them into the shape or design that we want is drastically different. We have a quick little video presentation to kind of walk you through the process. Check this out. So to make the comparison, we'll fire this up real quick. You can actually see an additive manufacturing process in action. Now this is a time lapse, sort of sped up a little bit, and this is a typical desktop 3D printer. But additive manufacturing, as you can see, allows for the creation of shapes without cutting. Whereas typical conventions, or typical manufacturing convention, is to take a stock of material and actually sort of cut it out. Additive builds up. I often make the parallel with taking a glue gun and using it repetitively over and over and drawing circles until eventually you create a cylinder. In this particular case, what you're seeing is a 3D model of a deer that is actually being printed off in probably PLA plastics. And as you see, it's sort of grown the creation. There wasn't any cutting, and there wasn't even any overhangs. There weren't any things that actually are typical with a conventional machine tool. There's no stock of material, for example, to be seen in the process. And as you saw, it started from the legs and it built up. And as it shaped the deer, it actually created the shoulders, the muscles, in essence of where they would be in a real deer. And that's an important part of this project, because we're going to look at how additive can allow us to grow things sort of organically, or design in organic nature. And what I mean by that is, if you take a look at a tree, you see a tree that has a lot more material near its branches at the joint between the trunk and the branch. Much like, we as human beings, we have more muscle around our shoulders and our joints and those kind of things. In the same case, in the deer, you can see how it's created. Now the process goes on until it finishes up the high detail at the very top, creating the antlers of the deer. And we'll just let it finish just to have. There we go. Sorry. So anyway, that is sort of a process and kind of how it works. If you're not familiar with it, this is one of the major benefits of additive. Another thing to keep in mind while it goes through it again is that if we were to conventionally make this deer in the same shape using typical subtractive manufacturing methods, we would have essentially had to get a chunk of material and carve out the deer shape, which would have been very complex, very possible, but very complex and very costly. Where in this particular case, it probably is just taking them out of, maybe cost the individual less than $1 probably to produce the part in terms of plastic, and however much machine runtime they have associated with it. So there's a quick little demonstration if you're not familiar with additive versus subtractive. So with that in mind, we kind of move on to the significance. There are no penalties associated with complex design for additive manufacturing, whereas we saw in conventional, or we talked about in conventional, it costs more and more to do more and more custom. Anything outside the norm gets broken down into more costly expense. You're seeing a build-up versus a break or cutting down. Obviously, there is reduced weight in production because we have an advantage of being able to print only or add material only where we need it, obviously material efficiency, and we're allowed to design more flexibly. Since we don't have to concern ourselves with how someone's going to conventionally make it, additive doesn't really care. It allows us more variation that we can do. And one of the major advantages in conventional manufacturing, the more custom you get, the more expensive it gets. The more features you have to add on beyond the norm, the more expense. So therefore, with additive, it doesn't really matter if it's super complex or it's super simple. The cost of production is always linear. It's just basically based on time and material that you need. And then there is the potential for on-demand manufacturing benefit out of this. So what we're going to do is, as mentioned, we're going to take the two parts and we're going to compare the differences. Now, in the conventional manufacturing, the part we'll design for it, we wanted to have our mentality about cost savings. So we're going to design the most simple design solution that we can to the problem, and therefore result in the minimum amount of cost. And we are going to assume that we can't actually buy this part anywhere, and then it's of sufficient size or limitations of size so that additive is a possibility of being used. And we're going to use on the AM side, we're going to actually design it to the most design variation we can. So here's the concept. Here is sort of what we're going to do. We're going to take a simple cantilever beam situation, a fixed end, and we're going to apply some kind of load. Now the top image you see there is our version of the conventional part to be made through subtractive manufacturing. We're basically going to create a basic shape, put loading on it, put a fixed end on it, and then we're going to compare the finite element analysis results with the actual organic version. Cantilever again, but you'll notice that we're going to sort of create internal structure in the design format. So we are going to assume in the process that in both cases we're going to use steel, typical steel that the software has built in, and we're going to use a basic parametric modeling package that comes with Autodesk Inventor 2013 because it's built in, because this is actually about finite element analysis and repetitive design features. This is kind of what we're going. So we want a process that we have a really good way to model in 3D and then turn around and get FEA results. As far as our yield stress goes, that's what we're going to use to be sort of our finish line between the two. Now, we're not going to really stress over hitting just dead on yield stress or being directly under. We're going to use that as sort of a benchmark to say we're in the ballpark of where we need to be, and yield stress, exceeding yield stress for is what the software says is where we're going to be our baseline for performance. So here's our basic dimensions. The overall part, 6 inches on one side, 4 inches on the other, and 20 inches long. A shape that's kind of lends itself well to cantilever beam design, so it's very, it has the advantage in terms of shape to begin with on conventional and additive applications. And just for quick terminology, we're just going to refer to additive on either as additive or AM, and conventional or subtractive as SM to keep things quick. So here's our two 3D models. As you can see, your top picture is your subtractive model, your SM model. Very basic, very bland. It is 1 inch thick, and both of them are 1 inch thick, and has no holes or cuts because that would add in cost. One of the other assumptions that we're doing with this is that the part has to be thick enough so that we can't just use a plasma cutter to conventionally make holes and shapes quick and easy. In the bottom, you're noticing the additive solution. Basically, your shape on the outside is about the same, but you'll notice a lot of filting and these very unconventional curves and splines. You see on the right image at the bottom, some of the organic nature of the curves and how they're not perfectly circular, they're sort of oval in places, and you're going to see why that's important here in just a moment. But these are your basic two models. Material conditions, this is just set up by the software with Autodesk. So their steel they consider somewhere around 30,000 PSI. So that works fine as long as we're using for both conditions. Your other features in there, you can kind of see those. So our overall conditions, boundary conditions though, of course we're going to fix the one end from all rotational movements or all rotations and all X, Y, and Z movements. It's completely fixed. And we're going to apply a 500 PSI top surface loading. Now we chose this to get a nice uniform result to kind of see how it stresses the overall part and to avoid any erratic sort of element stresses that are sometimes pop up when you do point loads. So this equates to around 10,000 pounds of loading on this particular part. We chose a moderate mesh density. Element size I believe was about 0.02, The reason we chose that size is it gives us good results, but at the same time it doesn't get too small. When we get smaller than that, we found the runtime to do the analysis was very lengthy, and since we're trying to do an iterative design approach with the additive process, we wanted something a little bit faster. Another thing that actually happens with Autodesk finite element analysis that we've seen is when you get too small of a mesh density, you run into more problems. So we decided to stay sort of out of that by using a moderate mesh size. Okay, so we take a look at our subtractive manufacturing part results. Here we go. We essentially have your basic results as we would anticipate with a cantilever beam loading. We've got our loading on the top that you can see right there, and our overall stress contour as you see moving back. Now this is first principle stress. We'll talk about why we're comparing those two in just a second. But you see a little bit of deformation on the right side, and as you would expect, this is the concentrated area of your higher end stress. One of the things I want to point out though is that you see in the blue, this is sort of the lower stress values, and there's a lot of blue. That's going to be key to our comparison in just a moment. Overall stress results, you'll see the first principle stress on our chart ended up running around 31, almost 32 KSI. So we're, obviously we are exceeding the yield stress, but we're in the ballpark. We didn't really want to go ahead and compare it back down. So third principle stress will factor in about the same, and we're in the ballpark of where we want to be to compare the two. Now our additive part results, you can see on the screen, a little bit different story. First of all, notice that our overall values were running at around 28,000 or 28 KSI. We will talk about the von Mises in just a second, but look at your stress distribution on the overall part. You'll see some concentrations in different areas. Obviously we have some at our fixed point top edge here, but we have more in these openings, a little bit of red and yellow in these zones, a lot of green, a lot of light blue, a little bit of concentration of dark blue to a higher negative stress value, and an overall coloration of we're using more material is the best way to say it. So the coloration on this one is more distribution of the stress, more evenly stressed components, and that's kind of what we're going for. This part itself actually ends up weighing about, or actually consumes about 40% less mass. It's about 38%, a little bit more exact, but we're in the ballpark of nearly 40% weight reduction overall, which is pretty significant. We'll go ahead and talk about the von Mises. You'll notice that there is a 51 KSI von Mises stress. This ends up being a sort of data error that we can point out a little bit later. So overall part results, we essentially got more bang for our buck, more material doing more in the overall part design, and where we don't need material, we removed it. You'll also notice this part has a lot more curved edges to it, a lot more filleting, a lot more features that are more rounded. And you'll even notice that a lot of the actual openings that we have here are very reflective of the stress curves that we saw, the contours of the curves themselves, the flow lines of the stress. We designed around that in the overall part creation. So as this part stresses, you're seeing some concentrations go this way and down in here, even some zones here. So you can see a lot of the design reflected the finite element analysis. And this was achieved by iterative design. So what we were going for is create the part, do the FEA, redesign the part. In fact, even the actual splines that were used to create the holes in it weren't even dimensioned. They were actually left open-ended where we could just pull and tug on the spline edges to create the shapes. And so this allowed for a rapid response to the finite element solution. And also the shapes are unconventional. And we weren't really concerned with, can it be manufactured? Can it be done? And in this process, that's a big deal, because normally in manufacturing you're interested in, can someone make the part? With additive, the machines don't really care how complex or how simple, so it almost always can be manufactured, or at least opens the door for a wide variety of designs. So as you can see here, these are all different stress results that ended up changing the shape. So features were added, the hole sizes were changed. You can see a difference between this one and in our final product. And you can see the stresses, how they were adjusted to compensate. So for example, here you see that the actual shape was more vertical in this case, And so to accommodate for the fact that there's a high stress concentration right there, you see that it was actually more buttressed or more angled out a little bit in that particular case. So further considerations, I did mention the von Mises stress associated with the AM part reduction or part creation. That was an error that we were getting when we could, I tried to get rid of it, but it was very persistent, so we just left it in there and ignored it. But what you can see here is basically a high concentration point right there, and it's right at the very edge. It's not realistic, and it was ended up being like 51 KSI, which would not really occur in real life, so just chose to ignore it. Another neat point about the process is that you can see we could add in features to the AM, because since it's AM, it doesn't require a bigger stock of material. It just builds up at the edges, kind of like it did with that deer. And as a result, what you're seeing here is the overall extension where we needed more material, and AM facilitated that. At the bottom of the part as well, this is what this image demonstrates. We just add a little feature to give us a little extra bump out in terms of what we need at strength down there, or material usage, and very simple change. Now, with that in mind, the question obviously would be, why didn't you do that for the conventional? Well, that would have required someone to either buy a bigger stock material and cut out a lot of material to get that bump out there and down there, which defeats the purpose of the cost savings with conventional. And also, or they could have welded it on, which still would have required more labor and more time. We also made the comparison of, could this part have been more basic, more rectangular in nature? So we actually did a conventional test of just basically doing a rectangle. I think it was 20 by 6, maybe 20 by 4, to kind of see if it could handle the load, and it actually exceeded stress there too. So obviously, no was the case there. There's a lot more finite element results, but we're just giving you the basics of the results. So in overall conclusion, obviously there's grounds for further study, and there's further consideration. For one thing, AM doesn't actually build solid internal structures like conventional ends up resulting in. So therefore, reality, would this perform exactly the same? Probably not, because software really aren't set up just yet for the internal differences of the layering effect of additive manufacturing. So internal performance on an additive has to be considered going further in research of this nature. But we did see that the organic response to the FEA results, and by organic we mean designing more organically, just pulling and shaping where you needed material, had a very large benefit. Obviously, near 40% weight reduction is a significant deal. And reduction of the waste associated with the conventional manufacturing, we weren't creating scraps, we weren't cutting material out. We only needed the material we needed, and there are sustainability benefits for something of that nature going further. So there's a lot to look at in terms of this particular report and our results, and I think it was very, very insightful in terms of a potential paradigm shift that additive manufacturing provides for designers. I mean, you basically can design with more freedom because you're no longer concerned with the subtractive manufacturing limitations. And the other benefit, of course, is that, lighter weight, less material has a great sustainability impact, especially in fields like aerospace and automotive and any type of custom work. So a lot of opportunities are coming out with the technology, and finite element analysis is a huge part of the process because it's back and forth. It's a check and redesign process that can yield great results. So thanks for your time, and we can provide any questions at a later point.